Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing, and this is lecture number 68, and we will start from where we have left in the previous lecture. So let me recapitulate just for your information's sake. NT by we're looking at N300, how this factor varies as a function of temperature we were just trying to see. And we saw that when our energy of the electrons is much smaller than that of the Fermi level at the source side, the fraction is almost equals to 1, which means that there is no change in the value of number of charge carriers with respect to temperature. However, we also saw that when Ex is near the barrier top, right, and therefore there is a heavy suppression of charge carriers at very low temperature, then the Nt by N300 falls off drastically in a low value, which means that the number of electrons available for carrier as a carrier to contribute is relatively much smaller, right, and therefore they have reduced impact on DIBL, because you can understand if the number of electrons are anyway less, right, then they will have a lower impact on the drain induced barrier lowering as well as SS at low temperature range. We now come to cryogenic temperature and doping analysis. The first part was basically looking at the carrier concentration with respect to temperature. Now we are looking into the cryogenic temperature and its doping analysis. So what we are looking is how does the cryogenic temperature gets affected by the temperature as well as NSD, which is source drain doping concentration, on DSDTs and thermal emissions for a nanosheet MOSFET. Now, if you look at the right hand side, this is basically current, which is normalized current. So, current at any temperature T, right, at any temperature T divided by current at 300 Kelvin is referred to as a normalized current, right. And of course, therefore, at 300 Kelvin, this whole anything you have will reach to a value of 1. Here, the channel thickness is taken to be 2 nanometer and the oxide thickness is 1 nanometer, and gate to source voltage is 0.15 volts and VDS is 0.1 volts, and we are plotting this normalized current versus temperature. Now, if you look very carefully, as the channel length goes on reducing from or increasing from 4 to 9, the current actually starts to fall, which means that a higher channel length current or higher channel length device will have relatively a smaller current with respect to 300 Kelvin. And the general trend is as the temperature drops down, that the current drops down. That's for sure, right? Now, but for a fixed value of temperature, even if you increase the value of your channel lengths, your current actually falls down in that case. So there are two axes here, and this is again, this side is the current, normalized current sorry, normalized current which you see here, and the left hand side is basically the 1 upon subthreshold slope which you see, and this value also sharply falls down as the temperature goes on reducing at a very fast pace. It is reducing. Now we will talk about a critical temperature. Critical temperature is that temperature which marks the onset of current saturation, that the current saturates almost and is independent of temperature at certain points at very low temperature. Now this TC is basically, which is known as the critical temperature, is decreases with decreasing source to drain doping. So as the source to drain doping concentration reduces, this the temperature at which the saturation starts also reduces. Why? Because at lower when you lower the doping, the potential drop extends over a larger region, right? And as a result, your effective tunneling length becomes larger and larger. The effect of increased tunneling length is similar to sort of analogous to increasing the channel length, and as a result your current starts to reduce with reducing the value of source and drain concentration. So you can understand from where is it coming. The source to drain, which are the dopant concentrations, when the source to drain dopant concentration starts to fall down, the resistance starts to increase, and effectively you require a larger TC in order to mark it. So when your TC decreases, your decreasing NSD also happens because of lower doping, right? And this effect of increased LT is similar to LT is basically my tunneling length, is similar to increasing the channel length in a sense. How does the current behave below the critical temperature? For high doping concentration, tunneling dominates, right? And this leads to a stronger current saturation. For very low doping concentration, current continues to decrease by 2-3 orders of magnitude below Tc. And therefore, with low NSD or low doping concentration, I would actually see a weaker tunneling effect happening, right. So, this indicates a lower or a weaker tunneling effect at lower NSD, right, and that is what we have understood in our previous case. Now, let us look at the same graph. We will again look at it from different perspective out of it, and we will be looking at the interpretation of Tc or the critical temperature. At high doping concentration, Tc clearly indicates that saturation is because of tunneling. At low doping, Tc, which is the tunneling critical temperature, should be seen not as a saturation on it, but the point where the thermionic emission exceeds the dsdt. Now, the exact value of Tc also depends upon the gate to source voltage, obviously, because gate to source voltage is responsible for drawing the current towards the channel, and that is the reason higher the value of gate to source voltage, you will see that the dependency of Tc actually starts to go on reducing. At higher VGS, Tc contribution increases, altering the balance between Te and tunneling, right. Now, let us come to the temperature dependence of saturation current as such, temperature dependence of saturation current. And if you look carefully here, then high doping concentration implies that the strong current saturation below Tc will be there. We are doing a fixed channel length of 4 nanometer, we are not changing the channel length here, and the doping concentration has been fixed to 4 into 10 to the power 20 per centimeter cube, and we are trying to find out the value of normalized current with respect to absolute value of current. We are trying to find out with variation in the value of the temperature, with TCH equals to 2 nanometer, T oxide is equals to 1 nanometer, VDS 0.1 volt and VGS equals to 0.15, right. So, basically we are in the linear region of operation, we are still not in the saturation region of operation. Now, in this case, because of high doping concentration, the tunneling current dominates, and therefore almost, so you see it is almost independent of the temperature. You see, this is almost independent of the temperature. They are almost flat with respect to temperature for when you consider very high doping concentrations of 4 into 10 to the power 20. When your doping concentrations are medium, there is a partial current saturation taking place. Both the thermionic and the tunneling currents contribute, and therefore there is a moderate temperature dependence which you can see. However, when you go to very, very low doping concentration, we have already seen in our previous slide that the tunneling decreases by a factor of 2 to 3 times below Tc, right. And tunneling current is weaker because what you have done effectively is that we have increased the tunneling length. When you increase the tunneling length, the tunneling probability reduces, right, and as the tunneling probability reduces, the tunneling current becomes weaker. So, we understand that if the tunneling is sharp is there, or a sharp tunneling barrier is there, then the probability of tunneling is relatively larger, whereas if you have a long tunneling probability or the TCH is large, then you effectively have PT which is much lower in that case, right, it falls down drastically. This is one thing which you should be aware of as far as when you vary the doping concentration, how does it varies the saturation current. Now, let us look at the transfer characteristics at high doping level. I am plotting ID versus VG for various values of gate voltage, and temperature is kept at 150 Kelvin and 220 Kelvin. The dotted curve is basically 220 and the full lines are basically 150. And of course, you can see at least in the lower values of VGS, 150 Kelvin temperatures has got a lower current as compared to 220, which is expected also. And we are assuming the source to drain the source drain doping concentration is very high, of the order of 10 to the power 20 per centimeter cube. At VGS equals to 0, the current are already nearly saturated with respect to temperature. We have seen that is of the order of few picoamperes which you get. That and therefore the tunneling current dominates at very, very low VGS values, right. At VGS equals to 0.2, somewhere in the linear region here, as you can point out here, 150 Kelvin almost shows, if not a saturation, the saturation swing almost sees a change, which means that it is almost linear, right. It is del ID del VGS, and if you look at this is basically a log scale which you see on the y axis. So, basically what we are getting is that the thermionic emission still dominates over the tunneling current. So, your tunneling current is much higher at very, very low VGS, but the reverse is true when you go to the moderate values of VGS, that lowering the temperature, therefore, what it shows is that the lower temperature shows a enhanced tunneling current, right. especially in the high doping level, and this leads to saturation of the current and the swing. Okay, let's look at the tunneling current density versus energy for different doping concentrations, which means that I vary the doping concentration and then I try to figure out the value of the current density with respect to energy. And this is the figure which is shown here and has got 3 doping concentration of 3 into 10 to the power 19. We have another 10 to the power 20, and we have the maximum one, which is 4 into 10 to the power 20. On the x-axis, the authors have plotted JDS upon EX, which means that tunneling current density with respect to electron energy here, right? So this is on the x-axis, you have dJ upon dJ, basically dJEX, right? This is drain to source tunneling density, rate of change of tunneling density with respect to electron energy, right? And as you can see here, that the highest value happens at the highest doping, EFS is highest, right? But E average becomes smaller than EFS, smaller than EFS. Now let's look at for the low doping concentration. If you see, you will see that your EFS value has shifted from this part to this part, whereas E average shift is very small, right? For NSD value, which means that the sharp of the peak of JDS by JEX is very large. For higher value of doping concentration, the shifts is relatively large. For the low doping concentration, the shift is really very small. Let's look at the effect of VDS on the tunneling energy, and this figure which you see here, at high doping level, both peak position and the average value of the energy are stable against changes in VDS, right? Which means that my currents and the SS swing saturation remains unchanged at these levels. At lower doping concentration, the peak shifts towards EFS, right, as VDS increases and reducing the difference between EFS and E average. So that will always reduce, right? And this leads to a relatively stronger saturation current at higher VDS compared to VDS, and this effect contributes significantly to the DIBL effect. So what the takeaway from this slide is that as you actually lead to a much higher concentration of source and drain region, your tunneling energy becomes larger and larger, and your average energy also increases. And you can see that the peak of JEDS-GX is also very large at that particular point. And we have taken here, remember that the channel thickness is just 2 nanometers, which is very small channel thickness I have taken into consideration while designing this. The oxide thickness is 1 nanometer and VGS equals to 0.15 effect. Now let's look at the subthreshold swing and DIBL effect together with varying values of VGS. Now we just now saw that the tunneling current begins to appear at low VGS and extends to higher VGS, and extends to higher VGS as temperature decreases. So as the temperature decreases, the tunneling currents effects gets available to you at higher VGS values. Now depending on device dimensions and operating temperature, 2 distinct values of subthreshold swings and DIBL can exist simultaneously in subthreshold transfer characteristics. So if you look at the right hand side figure, this plots current versus VGS, right? And if you look very carefully, the black current is my thermal. This is my tunneling current, the blue one. Then this filled rectangles, red rectangles are basically simulated. IDS is the red full line, and IT is the thermionic, and ITE is basically my tunneling current. Now as you can see here that the total current is basically coming up, but if you look at the lower one is a VDS of 0.1 and upper one is approximately 1 volt. And if you look at the slope of these 2 lines, basically they are almost the same in both the cases, right? And therefore there is no much change at very low values of VGS, but at the slightly higher values of VGS you will actually see a change, and DIBL can exist in that region. Then the transition between the tunneling dominated and the thermionic emission dominated region is clearly visible, where this part, right? If you look very carefully, this is the part where this happens. And the wavelet approach is much more better, where you self-consistently solve the Poisson equation, and the Schrodinger wave equation is superior match with any NEGF simulations, and that validates the approach. And now what we have seen therefore is that even if your channel lengths are longer, right, they are longer, and when if the channel thickness is sufficient, you will still have some tunneling current available to you. It cannot be ignored. It might not be very substantially large, but nonetheless it contributes to the total current flowing through the device. So you need to understand that part pretty clearly, that the contribution is still there for the tunneling current. Now, let us look at the wavelet methodology of transition of tunneling to thermionic emission with VGS. We are plotting again the same graph for various values of VGS. We are starting with 0.14 up to 0.4242. The blue is for 0.14 and the red is for 0.42. So, as the gate voltage goes on increasing, the peak of JDX, JDS, JX also starts to shift towards a lower electron energy, which means that as the gate voltage increases, the peak at which you will get a larger amount of current, right, will shift towards a lower value of electron energy. So, I will get a lower value of electron energy here. So, sorry, at low VGS, the tunneling dominates the current spectrum, which is evident from the tunneling current peaks which is available to us. So, if you look at carefully here, it is a low current tunneling peak here, but as you move towards the left, there is a sudden increase in the peak value, almost reaching to 1 value, normalized value reaching to 1, which is quite high. And as VGS increases, the contribution gradually shifts from tunneling to a thermionic, right. With increasing values of VGS, the saturation tends to happen for tunneling and the thermionic emission tends to gain out of it, right. Out of it means it gains out of the loss which it makes. And the figure therefore confirms the tunneling and thermionic contributions, they merge seemingly, and there is no abrupt change in the value, and therefore there is constantly a current and swing behavior which is proper. What we will do is we will look at the channel length dependency swing for different doping level, and what we will do is we will plot subthreshold slope versus channel length for various values of doping concentration, right. This doping concentration. At higher doping concentration, tunneling length is reduced, leading to a sharper transition, sharper and steeper transitions from thermionic to tunneling current. And this is more pronounced at lower temperature where the tunneling dominates. So, to take away from all this discussion is that at lower temperature the tunneling dominates, at lower gate voltage tunneling dominates. As you increase the gate voltage, the thermionic dominates, right. Now, and the swing increases due not only to tunneling current reduction, but also because of a sharper tunneling contribution at high doping. And that is because of the fact that you do have channel length dependent swings for different doping level. Similarly, let us go from these figure D, E, F, and as you can see here. So, at a long channel length, the DIBL effect that is expected also, because this is nonetheless a very short channel length formulation. So, at long channel lengths they all show a DIBL equals to 0. So, this is for 300 Kelvin, this is for 150, this is for 75 Kelvin, right. So, if you go to 300 Kelvin, you will see that the drain current and the thermionic currents are almost they are almost latched together, whereas if you go to 75 Kelvin, the dotted one, which is basically the tunneling current, that changes, thermionic current is very, very low at temperature, and the other one goes on increasing, as you can see here. And therefore, with decreasing temperature, a sharp transition from thermionic to tunneling occurs, followed by a nearly constant slope until the thermionic induced DIBL is introduced, right. Now, let us look at the temperature dependent swing for different channel lengths. Now, so the first graph is basically subthreshold swing versus temperature, all the three graphs. But what we have done is that we have, in this case, how does it vary with respect to temperature is what we are seeing in all the three diagrams in this case. And the first one is for channel length of 4 nanometer, the next one is for 6, and the last one is for 9 nanometer. At lower doping levels, the subthreshold current does not saturate with decreasing temperature, whereas for higher doping level it does that, because with higher doping level anyway resistivity is so small that saturation takes place very fast. Okay. Now, let us look at the temperature dependent subthreshold swings for different channel lengths. The same discussion is following for 9 nanometer. At extremely low cryogenic temperature, when temperature is less than 25 Kelvin, saturation current and swings are forced to become saturated, and because the E average and EFS distance are very, very small, and therefore they tend to average out, and that is being shown here at this particular point. In this particular point, you can see all these graphs are almost becoming saturated at very low values of temperature. Then we have a temperature dependent DIBL for different channel lengths for 4, 6 and 9, and the DIBL, obviously, that if you go, for example, at 9 nanometer, the DIBL is almost flattened out. At the high doping levels, both the current and swing saturates at temperature. At lower doping concentration levels, swing remains stable, but the current reduction with decreasing temperature is lower at lower VGS compared to the values of lower VDS values, right? Then VDS shifts towards the tunneling peak and E average becomes closer to EFS, as we discussed in the previous figure, and therefore DIBL at lower doping level continues to change with temperature, whereas in higher level saturation occurs for the doping level DIBL effect. So with this, let me recapitulate what we did for the next half an hour here. We looked into temperature dependency on the DIBL and thermionic effect, subthreshold slope. Two parameters, short channel parameters, are there affected by doping concentration of source drain. And we also looked into the temperature dependency of various second order effects which come into picture. And we saw that what is the dependency of thermionic emissions and tunneling with respect to temperature in this subject. I hope you enjoyed the lecture, and this probably is my last lecture with you all for this course. I sincerely hope that you must have enjoyed learning the course as I have been bringing it in front of you. It was a learning process for me as well, because when we write down these course and do all sorts of PowerPoint presentation slides with my TAs, we also learn many new things out of the whole process. I hope it's a mutually learning process for both you on the other side of the laptop and me as a faculty teaching this course. And of course, we will have some query sessions. We have a live sessions repeatedly within this course structure, and you can take help of and put up your questions so that we can answer those questions properly as far as the subject is concerned. I sincerely thank you for your hearing and looking at the course. I will be happy to receive feedbacks which will be helpful to make the course further better in coming years. Thanks once again to all of you, and happy learning.